Good evening, students. So, in previous lecture we have discussed about electrical capacitance of a parallel plate capacitor and the principle of a parallel plate capacitor with the behavior of dielectric. And when we consider the principle of a parallel plate capacitor, we mainly say when we bring a uncharged plate connected with earth to a charged plate, then the capacity of the charged plate continuously increases. Okay? And for a parallel plate capacitor, we mainly says it consists of two plates parallel to each other consisting of equal and opposite charges. That is why the total charge for a parallel plate capacitor becomes 0. Okay? And when we measure the electrical capacitance of a parallel plate capacitor, we find the electrical capacitance of a parallel plate capacitor mainly depends upon the area of the plate and distance of separation between the plates. Okay? And the electrical capacitance that we find C equal to epsilon naught A divided by D. Okay? So, this up to this portion we have already discussed in our previous lecture. Okay? So, in this lecture we mainly study what happens to the capacity of a parallel plate capacitor if you introduce a dielectric slab in between the plates of the capacitor. Okay? So, as we have already discussed in case of electric charge, when we place a dielectric material in between the charge, then electric force as well as electric field continuously decreases. Okay? But in case of electrical capacitance, let us see what is the behavior of a dielectric on the electrical capacitance. Okay? So, mainly we discuss about the effect of dielectric on the capacitance of a parallel plate capacitor. Okay? So, capacitance of parallel plate capacitor with dielectric slab between them, between the plates. Okay? So, capacitance of a parallel plate capacitor with dielectric slab between the plates, or we can say effect of dielectric on capacitance. Okay? So, in order to prove the or in order to observe the effect of dielectric on capacitance, let us first consider the parallel plates each of area A containing equal and opposite charges separated by some distance d, and at first we assume that in between the plates there will be some air medium. Okay? So, let us take first condition. There it consists of two plates each of area A. Okay? Each of area A. Area of both the plate is A containing equal and opposite charges of magnitude Q separated by distance D. Okay? And if the medium between the plate is air, then we can clearly say the capacitance, suppose we take C0. Okay? C0 is the electrical capacitance when the medium between the plates is air. Okay? So, capacitance of a parallel plate capacitor with air as medium is C0 equal to epsilon naught A divided by D. Okay? A is the area of the plate and D is the distance of separation between them. Let us put it equation 1. Okay? Now in case of second part, if you introduce a dielectric slab, okay, and we must introduce a dielectric slab whose thickness is first small than the distance between the plate, okay. In the first case we consider the thickness of the dielectric slab is less than the distance between the plates, okay. In later case we will consider if the thickness is equal to the distance of the plates, then what happens to the capacity, okay. So at first we case, let us introduce a dielectric slab in between the plates of the capacitor, and suppose the thickness of the dielectric slab is T, okay. The thickness of the dielectric slab is T, okay. Thickness between the plate of thickness of the dielectric slab is T, okay. And when we replace a dielectric by dielectric slab, then what happens? We know there will be some electric polarization, and because of that polarization the negative charges appear at the one face of the dielectric which lies toward the positive side of the parallel plates, okay. Then second thing, the positive charges aligns on the opposite face of the dielectric slab, okay. And because of this electric polarization there is induced electric field that produce in between the plates, okay. And suppose that induced electric field is P, EP, the induced electric field is EP, okay. And when there is a air medium in between the plates, suppose the electric field is E0, electric field is E0, okay. So if you observe the condition, if we, in order to measure the electrical capacitance, first we have to measure what is the net potential in between the plates, okay. We have to measure the total potential in between the plates, okay. So when we measure the total potential, then we can easily observe the total potential here divided into two main parts, okay. One potential will rise because of the dielectric material, and the another potential will rise because of the free space, left in between the parallel plates, okay. So when we measure or when we place the dielectric, then we can say the reduced field. What is the value of reduced field? Reduced field will be inside the dielectric slab, that is E equals to E naught minus EP. E equals to E naught minus EP, okay. And there will be two different potential that produce because of the dielectric. One potential is in between the plates of the capacitor that arises because of the reduced field E, okay. And this reduced field, everyone know value of potential V equals to how much? Electric field times the distance, electric field times the distance. I take here R, V equals to ER, okay. And the potential for the dielectric slab, okay, the potential for the dielectric slab depends upon the reduced field E that acts within the thickness T, And another things, the electric field, that is the left space in between the plate, that potential arises because of the electric field E0, okay. Means we can say the electric field E0 is acts between the left space, acts for the left space between the parallel plates, that is within the distance within the distance of d minus t, within the distance of d minus t. So, electric field E0 acts within the distance of d minus t. Okay, if you replace the total distance is d, dielectric slab thickness is t, so left space between the plate is d minus t. Okay, and electric field electric field E, that is the reduced field, that we can write E equals to E naught minus EP. The reduced field E acts for the thickness T. Okay. So, the resultant potential, okay, the resultant potential we can write here. What will be the value of resultant potential? Okay. So, the net potential for the parallel plate capacitor with dielectric is V equals to, okay, V equals to, for this space the potential will be E0 d minus t, E0 d minus t, because formula of V is V equal to electric field times the distance plus second potential is ET, second potential is ET, E acts for the thickness T, understand, but we know K equals to E naught divided by E, E naught divided by E. So, if K equal to E naught divided by E, then we can write E equals to E0 divided by K. Okay. So, replace value of E by E0 by K, and K is the dielectric constant. Okay. So, that is why the potential V equals to E naught d minus t, E naught d minus t plus E0 divided by K into T, E0 divided by K into T. Okay. So, we can take a common of E0. So, that will be E0, if we take common, the value will be d minus t plus T divided by K. Understand? Okay. But if we consider the plates has a surface charge density of sigma, plate has a surface charge density of sigma, and we measure in between the plates, we measure the effect in between the plates. So, that is why the electric field E naught that equal to sigma divided by epsilon naught, So, that is why we can write V equals to sigma by epsilon naught d minus t plus T divided by K. Okay. Again, what is sigma? Sigma is the surface charge density, and sigma equal to, we can write Q by A. Q is the charge, A is the area of the plate. So, Q divided by A. Okay. So, that is why we can write V equals to Q divided by epsilon naught A whole into d minus t plus T by K, d minus t plus T by K. So, this will give the potential in between the plates of the capacitor. Understand? So, what will be the value of capacitance? We know capacitance is charge divided by electric potential. Okay. So, the capacitance in between the plate of the capacitor will be, so capacitance C equals to Q divided by V. V is the net potential. Okay. Q divided by V. So, that will give C equals to Q divided by epsilon naught A d minus T plus T divided by K. Okay, so if you cancel the charge, that is C equals to epsilon naught A divided by D minus T plus T by K. Okay, so this will be the value of electrical capacitance when we introduce the dielectric slab in between the plates. Okay. So, if we take the variation like for the relation, if we take the relation, we can also reduce the expression like C equals to epsilon naught A, C equals to epsilon naught A divided by, okay, D minus, if we take a common here, T 1 minus 1 by K, 1 minus 1 by K. Okay, put this equation as equation 3. Okay, so that implies to C equal to, okay, take common of D. Okay, so if you take a common of D, then the value will be 1 minus T divided by D 1 minus 1 by K. Okay, and this value epsilon naught A by D, that is the electrical capacitance when the medium is air in between the plates. Okay, so this expression will reduce to the value that is C equals to C naught from equation 1. Okay, C naught whole divided by 1 minus T by D whole into 1 minus 1 by K. So you can remember also this formula in terms of capacitance with air as a medium in between the plates. Okay, so if you observe the case here, we can find C is greater than C0. C is greater than C0. Okay, C is greater than C0 for this expression. Okay, so now if we place the dielectric slab in such a way that it will cover the total space. Okay, if we place the dielectric totally cover the space in between the plates, then what happens? Case 1, if the thickness of dielectric is equal to space between the plates, means we can say if the dielectric slab totally cover the space in between the plates, that is D equals to T, the thickness equal to the space between the plates, then what happens if you substitute here? Okay, so if you substitute D equals to T here, so equation, put this as equation number 4. Okay, so equation 3 becomes C equal to epsilon naught A divided by D minus D plus D divided by K. Okay, so that's why C equals to epsilon naught A K divided by D. Okay, so that implies to C equals to C0K, if that is C equals to C0K. Okay, so what happens? What does relation predicts? This relation predicts that C greater than C0. That means the capacity of the parallel plate capacitor increases when you introduce a dielectric slab in between the plates. Understand? Okay. Okay, why this expression arises? Always K is greater than 1. Okay, K is always greater than 1. You can write here as K is always greater than 1. Okay, so as k is always greater than 1, this expression indicates the capacity of the parallel plate capacitor increases as we introduce a dielectric slab in between the plates. Okay. Now another case we can take, that is if we place a metal, okay, if we place a metal in between the plates of the capacitor, case 2, okay, if we place a metal in between the plates of the capacitor, in between the plates of the capacitor, okay, then what happens? For metal, k equals to infinity. For metal, dielectric constant is infinity, and if you substitute here k equals to infinity, this term becomes 0, okay, and the electrical capacitance will be C, that equals to epsilon naught A divided by d minus t. So this will be the electrical capacitance when we place a metal in between the plates of the capacitor. Understand? Okay. Now if you observe this expression, how can the dielectric constant can be defined? Okay. So write definition of dielectric constant in terms of electrical capacitance. Okay, I think all of you understand wow, the capacitance of a parallel plate capacitor behaves or depends on the dielectric slab. Okay, and you find the relation indicates that the capacitance of a parallel plate capacitor increases when we place a dielectric slab in between the plates. Okay, so dielectric constant in terms of electrical capacitance. Definition of dielectric constant. Definition of dielectric constant. Okay, so we get C equals to C naught K. C equals to C naught K means K equal to C divided by C naught. Look here, that is the slight change. There is a slight change, that is C indicates capacitance in a medium to the capacitance for free space. But in case of electric field and electric potential, electric field and electric force, we find capacitance in air divided by field in air to the field in a medium. Okay, there is a change. So dielectric constant is defined as the ratio of dielectric constant is defined as the ratio of capacitance in a medium to the capacitance in free space, Understand? Okay. So now let's measure the value of electrical capacitance. Okay, the value of energy stored in a capacitor. And before taking the energy stored in a capacitor, first we have to know the energy stored in a capacitor depends upon the flow of electric charge. As we know, the electrical capacitance always depends upon the flow of electric charge and production of potential difference. Okay, so write energy stored in a capacitor. Energy stored in a capacitor. Okay, so let's assume a parallel plate capacitor each of capacitance parallel plate capacitor of capacitance C is connected to a battery of potential difference V, connected to a battery of potential difference V. Okay, and because of this plate becomes positive charge, this becomes positive and this becomes negative. Okay, and energy stored is a measure of work done by the electric charge. Okay, energy stored in a capacitor is a measure of work done by the capacitor, we can say the measure of charging a capacitor is equal to energy stored in a capacitor. Okay, so what is the energy stored in a capacitor? The measure of the work done during the process of charging a capacitor is known as energy stored in a capacitor. The method, the work done during the process of charging a capacitor is known as energy stored in a capacitor. Okay, suppose in order to measure the energy stored in a capacitor, we first assume there is a small moment of charge. Okay, that is dq. Suppose that small charge is considered as dq in order to charging the capacitor. Okay, and when the charge dq moves, there will be a small work done, suppose with that dw. And what is the value of work done? Everyone knows W equals to V equals to W by Q. So W equals to VQ, potential times the charge. And what is the potential here? The potential difference is V, capacitance is C. Okay, suppose dq charge flows for charging a capacitor, such that work done dw equals to what? That is V dq. dw equals to V dq, but V is the electric potential. Okay, and you know V equals to, if C is the capacitance, C equal to Q upon V. So what is the value of V? That is Q divided by C. So that implies to dw equals to, substitute V as Q by C of dq. Right here V equals to Q by C. C is the capacitance of the plate. Okay, so if we flow a charge of capital Q, okay, if we flow a charge of Q0 to Q equal to capital Q up to limit Q equal to 0 to Q equal to capital Q, then what will be the resultant work done? Okay, so measure the total work done by flowing the charge from Q equals to 0 to Q equal to capital Q is given by is given by W equals to integration dW 0 to W, and 0 is the work done when there is no flow of charge, and W is the work done when we flow capital Q amount of charge. Okay, so that's why W equals to integration 0 to capital Q, substitute the value of dW, that is Q by C into dQ, Q by C into dQ. So C is the capacitance, C is the capacitance, and we are taking a constant electrical capacitor. Okay, so W capital Q is equal to, right here, is equal to energy, is equal to energy stored in the capacitor, energy stored in the capacitor, that is U equal to W, U equal to W, small u, write this as small u. Okay, so small u equal to W, so that implies to U equals to 1 by C, what is Q dQ integration, that is Q square by 2 limit 0 to capital Q. Okay, so U equal to, that will be give 1 by 2 Q square divided by C, take as equation 1, take as equation 1. So that is the energy stored in a capacitor in terms of charge and potence, charge and capacitance, को term रे नहीं छो, the charge और capacitance. Okay, and we can also convert this expression in terms of different form. Okay, but write this as equation 1, but Q equals to CV. If measure Q equals to CV, from this expression Q equal to CV, so U equals to half, that is C square V square divided by C. So U equal to another expression, that is half CV square, half CV square. Okay, that is the expression in terms of capacitance and potential. Okay, again C equal to Q by V, C equal to Q by V, C equal to Q by V, so U equal to half QV, U equal to half QV. Okay, this is the another expression. Okay, in terms of charge and potential. So as a whole, if you write the three expression, that is equation 2, if we write equation 1, 2, 3 in combination form, okay, so the total expression will be energy stored in a capacitor, that equals to half CV square equal to half Q square by C equals to half QV, equals to half QV. Okay, so this will give the value of energy stored in a capacitor. Understand? Let us measure energy density. Okay, energy density in terms of electric field intensity, energy density in terms of electric field intensity. Energy density in terms of electric field intensity, electric field intensity, energy density in terms of electric field intensity. Okay, so when we measure the energy stored in a capacitor, we find the energy stored is half CV square. Okay, and if you assume in between the plates there is the electric field E, in between the plates there is some electric field E, then we can say the energy density of the capacitor definitely depends upon the electric field intensity in between the plates. Okay, energy, what is energy density? Energy density is energy per unit volume. Okay, everyone know energy density is total energy or simply energy per unit volume. Energy per unit volume. Energy per unit volume, and simply we write energy density as capital U. Write energy density is capital U. So energy density U equals to energy per volume, that is small u divided by V. Small u divided by V. Energy per unit volume is called energy density. Okay. For a parallel plate capacitor, what is the value of energy? Okay. But for parallel plate capacitor, U equal to half CV square. U equal to half CV square. Energy U equals to half CV square. So that implies to convert this in terms of electric field. Okay, convert this in terms of electric field. Everyone knows for a parallel plate capacitor consisting of opposite charge separated by a distance d, electric field suppose that is E. Okay, then the electrical capacitance, that is C equal to epsilon naught divided by d, epsilon naught A by d. And what is the electric potential? V equal to electric field times distance. V equal to electric field time distance. Okay, substitute these two values. Okay, so U equals to half C, that is epsilon naught A divided by d into V square, that is electric field times distance, that is E square d square. Okay, so that will give U equals to half epsilon naught A, half epsilon naught E square A into d divided by d, half epsilon naught E square A d. Okay. So if we use this expression here, so what will be the value we get? Substitute. So energy density U equals to energy by volume. Energy by volume. What is A? A is the area of the plate. What is D? D is the distance between the plates. Okay. So 1 by 2 epsilon naught E square A d divided by volume. Okay. Volume. V is the volume. Volume is equal to volume. V equals to, what is the value of volume? Volume V equal to area into thickness. Area into thickness. Okay. So that's why we can say 1 by 2 epsilon naught E square AD divided by AD. Okay. So if we cancel these two expression, what will be the energy stored? Half epsilon naught E square. So this will give the expression for energy density in terms of electric field. Okay. So now let us discuss combination of capacitors. Okay. So here we measure the electrical energy stored in a capacitor. So now discuss an important thing. This one is very important, that is grouping of capacitors. Okay. That is very important, grouping of capacitors. Grouping of capacitors, or we can say combination of capacitors. Combination of capacitors. Grouping of capacitors or combination of capacitors. Okay. So when we consider grouping of capacitor or combination of capacitor, mainly we take two type of combination. One is series combination and another one is parallel combination. Okay. So firstly, the combination of capacitor is two types. Okay, here we consider two type of combination. One is series combination, series connection. Second, we take parallel connection. Second, we take parallel connection. Okay, one is series connection, another one is parallel connection. Okay, if we join a number of capacitors, over one wire, then the combination becomes series combination. Okay, and if we place the capacitor on different wire connection, then the combination becomes a parallel combination. Let's understand what does the series and parallel combination says. So first we understand series combination or simply series connection. Okay, series connection of electrical capacitance says if a large number of capacitors connected in series, then the combination becomes a series combination. Okay, so if we arrange a large number of capacitors in series, okay, suppose we take there is a large number of capacitors arranged like this. Okay, so these are the capacitors, they are arranged over one wire and connected over a battery of potential difference V, connected over a battery with potential difference V. Okay, then what happens? Suppose these are the capacitor of capacitance C1, that is capacitor C2, that is capacitance C3, and that is capacitor Cn. Okay, and this one is positive and this one is negative, means this plate becomes positive, this one becomes negative. Again this one is positive and this one is negative, plus this one is plus, like this. Okay, and there must be one things to observe. Each capacitor, the resultant potential is V. The resultant potential is V. But for each capacitor, there will be certain value of electric potential difference. So I take here the points. Most important these points. Okay. Okay. So between each points, there will be some electric potential difference. Suppose that is V1. And that is V2, that is V3, and that is Vn. Okay, each capacitor is connected over one wire, so they create small potential differences. Potential difference for capacitor C1 is V1, potential difference for capacitor C2 is V2, potential difference for capacitor C3 is V3, and potential difference for capacitor Cn is Vn. Okay, and as all the capacitors are connected over one line, so they must operated over a common charge Q. All the capacitor must be maintained over a constant charge Q. Okay, so that's why there will be net potential arises, which is equal to sum of the potential due to each capacitors. Okay, the net potential is equal to sum of all potentials produced by the individual capacitors. Okay, and one thing to observe that for series connection, all the capacitor maintained over a constant electric charge. But each capacitor will produce different electric potential. So as each capacitor produce different electric potential, so net electric potential, what will be the net electric potential? Net potential is the sum of all the potentials produced by individual capacitors. So that is V1 plus V2 plus V3 plus Vn. So that will give the net potential. But one thing to observe, if C1 is the capacitance with potential difference V1 maintained over a charge Q, so what will be the expression? V1 equal to Q by C1. V1 equals to Q by C1. Okay. But one thing to observe, for capacitor C1, what is the value of V1? V equals to Q divided by C1. Okay. What is the value of V2? V2 equals to Q divided by C2. Okay. As all the capacitor maintain over a constant charge, for series connection, charge is constant. Okay. V3, that is Q divided by C3, and like this Vn equal to Q divided by Cn. Q divided by Cn. If we measure the total capacitance for this combination is Cs. Okay, if we measure the total capacitance for this combination is Cs, then what will be the value? Okay, if we assume if Cs is the effective capacitance, effective means the total capacitance, effective capacitance of the combination, effective capacitance of the combination maintained by the potential difference V, then V equal to Q divided by C. V equal to Q divided by C. So substitute the values here. Okay. So thus V equal to V1 plus V2 plus V3 plus Vn. Okay. So that implies to value of V, that is Q divided by Cs. Okay. Q divided by Cs equal to Q divided by C1, okay, plus Q divided by C2 plus Q divided by C3 plus Q divided by Cn. Understand? So take common Q. So Q divided by Cs equal to, if you take Q common, that is 1 by C1 plus 1 by C2 plus 1 by C3 plus 1 by Cn. Okay, so that is 1 by Cs equal to 1 by C1 plus 1 by C2 plus 1 by C3 plus 1 by Cn. So what does the effective capacitance says? For a series connection, the effective capacitance, okay, the effective capacitance reciprocal, is equal to the reciprocal of all the capacitor or algebraic sum of reciprocal of all the capacitors due to individual, all the capacitance due to individual capacitors. Okay. So what does we can define from this series connection? So write this, all are in continuous form. So 1 by Cs equal to summation, this expression is important. Remember this, 1 by Cs equal to 1 by C1 plus 1 by C2 plus 1 by C3 1 by Cn. All are lies in the reciprocal form in series combination. So 1 by Cs equal to summation n equals to, or summation n 1 by Cn. Summation n, that is 1 by Cn, or simply write summation of I equal to 1 to n 1 by Ci. Okay. So what does the series combination says? Okay. So for the reciprocal of effective capacitance is equal to the algebraic sum of reciprocals of capacitance of individual capacitors. Okay. So, the reciprocal of effective capacitance is equal to the algebraic sum of reciprocals of capacitance of individual capacitors. This is known as law of series connection. Understand? Okay, so all lies in the algebraic reciprocal format. So let us measure law of parallel combination, second grouping, that is parallel combination. Okay. Parallel connection. Okay. So, parallel connection, all the capacitor must connect over different wires. Okay, they must connect over different wires. Okay, a parallel combination is like, suppose this one is my battery of a potential difference V and potential difference V, one plate is positive, another plate is negative, and from this point, look at, from this point, in between the points the potential difference V, in between the points the potential difference is V. Okay, so let us divide this wire into a number of wires. Okay, let us divide this wire as number of wires, and over each wire we connect a capacitor. Over each wire we connect a capacitor like this. Okay. Suppose this one is capacitor C1, this one is capacitor C2, this one is capacitor C3. Okay, and dot dot, this one is capacitor Cn. Okay, this one is capacitor Cn. Okay, and all the capacitor operated in between two common points having potential difference V. Potential difference V. Okay, suppose this one is the charge, this one is the charge Q. Okay, and if we observe, this one is plus, this one is minus. Okay, and the total charge here, the total positive charge here divided into a number of positive charge Q1, this one is Q2, this one is Q3, and this one is Q4, like. And also the total negative charge minus Q, here also divided in minus Q1, minus Q2, minus Q3, and like minus Qn. So in case of parallel combination, what happens? There is a division of charge. Okay, point to mark. In case of parallel combination, there is a division of charge with a constant potential difference. In case of parallel combination, there is a division of charges with a constant potential difference, but in case of series, there is a division of potential over a constant charge, but here there is a division of charges over constant electric potential. Okay, so when we take the measure of total potential for the parallel combination, we can start from measuring the total charge of the combination. The total charge Q is the algebraic sum of all charges, that is Q equal to Q1 plus Q2 plus Q3 plus dot dot Qn plus dot dot Qn. Okay, but for this capacitor C1, potential difference is V, charge is Q1. Potential difference is V and charge is Q1, and everyone know Q equals to CV. Everyone knows Q equals to CV. Okay, so that's why Q1 equals to C1V. Q1 equals to C1V. Q2, what is Q2? Q2 is maintained over potential difference V and charge is Q2, that is C2V. Q3, that is C3V. Like this, Qn equal to CnV. Understand? But if we measure the total effective capacitance as Cp, okay, parallel combination, if Cp is the effective capacitance of parallel combination, then we have Q equal to Q1 plus Q2 plus Q3 dot dot Qn. So substitute the values. Okay, then right here complete this term, then Q equals to CV. Okay, Q equal to CPV. Q equal to CPV. CP is the effective capacitance, V is the total potential. So Q equal to CPV. Substitute. Okay, we have Q equals to, that is CPV equal to C1V plus C2V plus C3V plus dot dot, that is CNV. Understand? Okay, take the common potential. Okay, Cp if equal to CPV equals to V, if we take common, C1 plus C2 plus C3 plus dot dot Cn. Okay, so if you take, that is Cp equals to C1 plus C2, cancel the potential, plus C3 plus dot dot Cn. So that will give the value of effective capacitance in case of parallel combination. And one thing to mark, in case of parallel combination, there is a simple algebraic sum. And in case of series, there is a reciprocal algebraic sum. Okay, or Cp equal to summation over I equal to 1 to n Ci. Summation over I equal to 1 to n Ci. That's why the law of parallel combination says the total effective capacitance of parallel combination, okay, the total or the effective capacitance for parallel combination, the effective capacitance for parallel combination is equal to algebraic sum of capacitances due to individual capacitors. due to individual capacitors. This is called law of parallel combination. Law of parallel combination. This is called law of parallel combination. That is, the total effective capacitance for a parallel combination is simply the algebraic sum of capacitances of all the capacitors. Okay. So, this is all about the grouping of or the connection of capacitors in series and parallel case. Okay. So, there is one little bit part that lies in the dielectrics. This is about the conductor and insulator. Everyone knows what is a conductor and insulators. Okay. This is the last part of the electric capacitance and potential. Conductors and insulators. Conductors and insulators. Conductors and insulators. Okay. What is a conductor? Simply we can say a conductor is a metal. Okay. It is a metal in which there is a large number of free electrons. Large number of free electrons lies on its surface to carry out the electric charge. Okay. Large number of free electrons lies on the surface to carry out the electric charge through them. Okay. Whereas insulators are the materials in which there will be no presence of free electrons to carry out the electric charge. Okay. That is why the conductivity or electrical capacity or electrical conduction capacity of conductor is very high than that of the insulator. Okay. And electrical conductivity of the insulator is 0. Electrical conductivity of insulator is 0. Okay. So, we can say conductors allow a large scale movement of electric charge through them. Okay. First we can say what is a conductor. Okay. So, conductors are the materials. Conductors are the materials. Conductors are the materials in which there are large amounts of free electrons, large amount of free electrons to carry out electric charge, carry out electric current. Okay. So, conductors are the material in which there are large number of free electrons to carry out the electric current. Okay. Means we can say it allows a large scale movement of electric charge through them. Okay. And because of large amount of free electrons, we can say these free electrons in case of conductor, these free electrons are called mobile charges. These free electrons are called mobile charges. Mobile charges means there is a capacity to carry the electric current. Okay. That is why, or they are capable to move. Okay. That is why they are called mobile charges. Okay. Another things we can say, conductors have large value of electrical conductivity. electrical conductivity. Okay, because of large free electrons, they possess large value of electrical conductivity in the order of 10 to the power 8, in the order of 10 to the power plus 8. Okay, electrical conductivity is very high in case of conductors. Okay, but when we observe an insulator, examples we can say copper, silver, okay, iron, all metals are conductors. Okay, iron, cobalt, iron, etc. Okay, but silver is a good material. Silver is a good material of electrical conductivity, but as the price of silver is very high, so that's why we use other materials like aluminum we can say aluminum, okay. Silver is best material for electrical conduction. Silver is best conductor or best metal for electrical conduction. Silver is best metal for electrical conduction because of high price of silver, we cannot use silver, we use aluminum or copper for the electrical conduction. Okay, so now widely used is aluminum and copper. Their price is cheap. So that's why we use that materials as electrical conduction property. Okay, so now let us take insulators. So what is an insulator? An insulator is a non-conducting simply material. We can say insulator is a non-conducting materials that do not have free electrons. Okay, that means insulators do not have free electrons. Do not have free electrons. Second thing, electrical conductivity is 0. Okay, means we can say very small. Okay, electrical conductivity is 0. Third things we can say, and because of unavailability of free electrons, we make electrical conduction for insulator by the process of friction. Okay, we can charge it by rubbing or frictional electricity. Okay, example we can say examples. What are the different examples? Wood, glass, okay, wax. These are the few examples of insulators. Okay, now let's take what is the behavior of a conductor in electric field. Behavior of a conductor in an electric field. Okay, behavior of conductor in electric field. Behavior of conductor in electric field, we put it as a point format. Okay, so when we place, suppose this one is a conductor. Okay, when we place a conductor in a uniform electric field, suppose this one is a uniform electric field, Okay, if we place a conductor in uniform electric field, what happens? The electric lines of force do not passes through the conductor. Okay, and the reason is that because of that electric field, all the charges aligned on the surface of the conductor. Okay, aligned on the surface of conductor because of application of electric field. Okay, when you apply the electric field, all the charges of the conductor lies on the this one is plus side, plus to minus, so this will becomes negative region and this becomes positive region. Arrow is left to right, plus to minus. Okay, so electric field is opposite. Inside the conductor there is a opposite electric field, that is called polarized electric field. So E net equals to 0. E net equals to 0. So you can say number 1 point, net electric field is 0 inside the conductor. Okay, so that means we can say conductor do not allow to pass the electric lines of force through them. Second things we can say that already we have observed in case of electric potential equipotential surface, a electric field outside the charged conductor is perpendicular to its surface. Second point, that is for a conductor, the electric field outside the conductor is perpendicular to its surface. Is perpendicular to its surface. Electric field outside the conductor is perpendicular to its surface. Okay. Third things we can say, observe here, when we place the conductor in a electric field, all the charges resides on the surface and surface acquires equal and opposite charges. Okay. As the surface acquires equal and opposite charges, the net electric field inside the conductor is 0, means we can say the net charge for this conductor becomes 0. So third point we can say net charge inside the conductor is 0. Number 3, that is net charge inside the conductor. Net charge inside the conductor is 0. Net charge inside the conductor is 0. Another things, for a conductor, it poses constant electric potential. For a conductor, it always poses constant electric potential. Okay. So electric potential of a conductor is always constant. Okay. Number 4, electric potential for a conductor, for entire conductor is always constant. That means inside on the surface. Okay, you may take inside or in the surface, the electric potential is always constant. Surface and inside point, electric potential always constant, because inside the conductor the electric field is 0, and when the electric field is 0, how can we prove this? You can take like dV equals to minus E dr. dV equals to minus E dr, but E equals to 0. Okay, it's E equals to 0, so dV equals to 0. So if dV equals to 0, what is V? So V becomes constant. V becomes constant. So electric potential for entire conductor is always constant. एटा मते जने डाउट रे पचारथिलो जे so how electric potential is constant. Okay, so electric potential for entire conductor becomes constant. That means inside or on the surface of the conductor the electric potential is constant. Okay, another point we can say all the charges for the conductor resides at the surface. Okay, fifth point, that is all the charges resides on the surface of conductor, on the surface of conductor. All the charges resides on the surface of the conductor. Okay, so that's why as all the charges resides on the surface of the conductor means we can say electric field exists at the surface. Okay, electric field exists on the surface of the conductor. Okay, so electric field exists on the surface of the conductor. Electric field exists on the surface of the conductor. Surface of the conductor. Electric field exists on the surface of the conductor, and when we measure the value of electric field, that equals to sigma by epsilon 0. Okay, that is we can say E vector equal to sigma by epsilon 0 n cap. The value of electric field on the surface of the conductor is E equal to sigma by epsilon 0 n cap. Understand? So these are the different points that we find for a conductor in a electric field. Net field is 0, inside the conductor is 0. Electric field outside the conductor is always perpendicular to the surface. Third things, all points are important. Net charge of the conductor inside the conductor is 0. Electric potential for the entire conductor is constant. All the charges resides on the surface, and electric field exists at the surface, and value of electric field is E equal to sigma by epsilon 0. So these are the important points for the behavior of a conductor in a uniform electric field. Okay, so this is all about your electric potential and electric capacitance. So in next we will discuss some of the problems on electrical capacitance depending upon the problematic calculation and also depending upon the combination of the capacitors. Okay, so thank you. So I think all of you get some idea about what the electrical capacitance says. Okay, thank you.